Hello, we're Team 10, and this is our final presentation on the analysis and redesign of electric water kettle. An electric water kettle is a covered container used to heat up water and boil liquid, usually water for consumption. Our production volume target is approximately 484,000 units per year. Our primary customers are avid coffee and tea drinkers that will use the electric water kettle to heat up water for their coffee and or tea, likely making only a few servings at a time. And our primary secondary customers are small business owners that will use the electric kettle to heat up large volumes of water to make up many specialty drinks quickly with little operating cost. Here is an exploded CAD view of our product, and we have 13 main parts. We created a fast diagram where our main function is provide water, and our primary functional branches are boil water and pour water with associated secondary functions. And to ensure dependability, we have the function of preventing burns with associated functions. Using the fast diagram and components from exploded CAD, the function component mapping matrix was created, where every part had at least one associated function. Looking at the fast diagram and varying needs of our primary and secondary customers, we created the function differentiation table, where we identified that the main function that stands out as a candidate for function differentiation was containing water, since the quality of water is a varying preference between customers. Hence, on our component commonality table, our module we identified was a steel kettle body, since this is the only part that involved the function of containing water, while the rest of our parts make up the platforms. The module part consists of two different heights of the steel kettle body, 7.1 inches versus 9.1 inches. And the next slide shows the common interface components for the modules, which consist of the lower base plate assembly, top lid assembly, and a plastic handle. The modified assembly sequence pulled ahead the base plate subassembly parts to allow the steel kettle body module part to be further delayed in the assembly sequence. This allows one variety to be maintained for the first three steps, as opposed to having two varieties at the start of the assembly. We've done a DfA manual analysis on our product, and our initial assembly time was approximately 200 seconds, with assembly efficiency of 16.3%. Looking at the quad chart, we identified analysis parts to be the glass lid, the steel kettle body, since these two parts had high functional importance with a high manufacturing assembly cost. Looking at the module part, we applied DfA 2, DfA 10, and DfA 11 by reducing the fastener holes from 3 to 2, added a chamfer, and added 4 protruding legs. Looking at the platform part, we applied DfA 1, DfA 10, and DfA 11 by merging parts, adding a chamfer, and adding hole bosses for plastic lid handle insertion. Looking at the redesigned parts, we decreased assembly time by approximately 45 seconds, increased assembly efficiency by 4.6%, and decreased total manufacturing cost by $1.60, since we deleted a part and merged two parts together. And there was no changes in the product function.
For our automated assembly, we selected the base plate subassembly, which includes the base plate cover, power circuit board subassembly, and fasteners. Looking at our functional mapping matrix, it was observed that the power circuit board and base plate shared the same singular function, which was to heat water. This was a clear opportunity for part consolidation. So for our redesign, we removed the base plate to reduce part count, then we eliminated the screws to reduce fastener count, and finally we added a snap fit to house the electronics. The original design cost $12.45 to automatically assemble, while the redesigned part costs only $8.33. There is expected to be minimal impact on product function, although the exposed electronic subassembly raises concern for the kettle's dependability for preventing burns. Overall, the redesign has an expected 33% decrease in manufacturing costs, as any additional plastic added to the base plate cover for the redesign is not anticipated to cost more than the base plate and the fasteners would in our original design.
So to move on to some process selection, the first piece that we redesigned is our steel spout. We have some dimensions shown off to the left, but our most critical dimension is the inner radius and arc length of this piece, because this is ultimately what's going to form the angle where this will attach to the steel kettle body, and we need this to be nice and tight because this is involved in pouring water, and we don't want water to leak out between the crease of this and the kettle body when it's used. So because of this, we gave it a fairly tight tolerance of plus or minus 0.01 millimeters. Our next piece is our plastic kettle lid, which we again have some more dimensions shown, but the most critical dimension is the outer radius. We need this to fit on top of the steel kettle body. It doesn't need to be watertight like our last piece does, so we gave it a little bit of a looser tolerance of plus or minus 0.1 millimeters. Looking at our candidate processes, for our spout we have sheet forming and machining shown in red, and for our lid we have machining and injection molding shown in blue. Both pieces have thicknesses that meet either of their candidate processes requirements, so this doesn't really narrow it down. Same goes for mass and for tolerance. Either machining or injection molding works for the lid. So we chose injection molding, but either would work. For the spout, neither of the primary processes meet this. So we opted to go for sheet forming and then go for precision machining to bring our piece down to tolerance. And this really solidified our decision to make the piece out of steel so that it is some type of metal so that we can bring it down to a tighter tolerance.
For the design for manufacturing analysis, we started with the sheet metal spout. Assuming a 1-year payback period, our pre-design for manufacturing cost estimate was assumed to be $0.106. This was calculated through the analytical method. Unfortunately, when we ran DfM Pro on this part, it gathered no results for improvements made. So we decided to redesign the part using principles from the lecture. We decreased the bend lengths and were able to make a shape that nests much better than the original part. We also added fillets to avoid sharp corners and got rid of the narrow feature on the old spout. You can see the isometric view with important dimensions called out. After the design for manufacturing, the cost estimate of the analytical method was reduced to 0.1482 cents. We used the instant price quote from Hubs as well. Unfortunately, Hubs did not allow us to use sheet metal as for the original spout, so we moved the manufacturing method to machining. The new redesigned part was kept with sheet metal as the redesign. We did some extrapolating of the data to show that the Hubs quote would be extremely small as compared to the analytical method. We did this by using multiple different quantities and extrapolating these few points into an equation. We then plugged the number of units into the equation and got the price. Unfortunately, with the Hubs quotes being different, as they two had different manufacturing methods, we can see that the after design actually has it costs more per part in the after design than the before design. For the other part, we analyzed the injection molded lid. Assuming a 1-year payback period, we used the analytical method to calculate a cost estimate of $1.848. You can see the cross section of the pre-DfM part here. Using DfM Pro, we were able to get suggestions for improving the manufacturability of the part. These included minimum radius at base of boss, minimum draft angle, uniform wall thickness, and mold wall thickness. Taking these ideas into consideration, we redesigned the part and got a new cost estimate of $1.373 from the analytical method. This decreased from the pre-DfM estimate, which is perfect. The new part with dimensions called out can be seen here. Additionally, we avoided sharp corners and side pulls and also minimized the wall thickness. We made the thickness as uniform as SolidWorks would allow. We also adjusted the draft angle as much as possible for DfM. You can see that after the redesign, we have addressed some of the issues that DfM Pro saw. There are still a few that could be addressed in future design iterations of this part.
Here we have our product, service system, and wrap-up. To improve our customer experience on our product, we plan to implement a surface finish on our kettle to make it easier to reuse and wash, as well as to have some corrosion resistance. We also wanted to reduce the environmental negative impact by offering a trade-in and recycle service to customers who are willing to replace their old kettles with new ones and dispose of them properly, giving them a discount to save on purchase costs as a result. Implementing an energy-efficient power source would help the customer save on electricity costs over the life of the product. We also plan to include a helpful user manual to guide and educate customers on how to improve the life of the product, therefore reducing the environmental impact. We also achieved multiple cost savings using DFA, manual and auto, and DFM, and we included some pros and cons of our design and what we'd do if we would start this all over again. Thank you so much.